think we have some people from the US who may even be extremely early morning. If you're there, could you maybe make a noise?
3 people from the US accepted. Maybe they join a few minutes later.
Okay. All right. So look, guys, we've been speaking in this workshop now for a couple of years, and I wanted to show very quickly the progress that's going on in the project. And I want to show this because I think as an INC team, you can see that things are happening, okay? And I think it's always motivational to know what's going on. So in the last year, we had a lot of arrivals onto the project. TF coils, vacuum vessel sectors, many different components. You can see here a vacuum vessel sector shipped from Korea. TF coil, this is one of the TF coils that's arriving. This is another TF coil. This is from Japan and Europe. This is a lot of stuff coming from Russia. A lot of stuff coming from, one second, I want to tag that. A lot. Then we have obviously stuff coming from China, India, and manufacturing, finishing, stuff already delivered from many of these countries. You see here again the TF coils. The TF coils are moving along. Obviously, we've got some, but there are many TF coils to come. But again, more vacuum vessel sectors. The next vacuum vessel sector is coming from Korea in roughly the end of April. So we've already got one, and the second one is coming. You can see the PF coil work is finishing in Russia. And you can see in the US, the solenoid is now really progressing well. After, many of these systems had many issues during their manufactures, and now they look to be sorted out and moving on. Again, you can see now here, this is the vacuum vessel in the pit. Sorry, not in the pit, in the assembly building. And this is where it will arrive very, very soon. And I'll show you a picture in a minute, but this is the assembly jig for the vacuum vessel sector, the TF coil, the thermal shield. Last year I showed you this picture, which is the neutron flux monitor for diagnostics coming from China. And now I can show you this picture because it's actually installed. It's literally in the building. It looks rather small when you see it in the huge tokamak area, but it's still quite a decent piece of equipment. This is the vacuum vessel sector being dressed by an engineer, obviously starting to put diagnostics on it. If you know all your details, you will see these little dots here are part of some coils that George is putting on. And then these are the coils on. And you can see they're covered over for the moment. This is signing off of the coils, so the job is done. So diagnostics installed all over ITER now. And this picture I got from George yesterday. Thank you, George. I think it's an absolutely lovely picture. It shows the vacuum vessel sector now ready to be picked up and actually put into the position, into that unit that I showed you a few moments ago. And here you can see all the coils, the OVC outer vessel coils, which have now been installed. This is the inside, by the way. Obviously, that's the outside, the equatorial port level, upper port level. This is the inside. You can see here the coils. Some of them are different angles for various reasons. And more than that, you can see the wires coming from the coils, and they're all joined up nicely and going along the outside. You can see this is all quite delicate. You have this enormous heavy vacuum vessel, and you've got these nice delicate wires, but they look like they're well attached. And this is good to see. So this is now getting ready, as George told me, to be hoisted and put into the equipment to assemble everything. There's very small gap between these coils and the thermal shield when they're installed. I mean, we're talking about very small gaps, so we hope that they survive, but they should be tough. Okay, this is another thing that's going on in the in-vessel wiring. This is a simulation. We have to connect a lot of wires inside the vessel, like thousands of wires, but there are many attachments to the vessel to keep the wires cool. It's a good feature, a new feature. You have a neutron heated tokamak. You need to make sure that you keep the wires cool. And these are all mineral insulated. They're all thermally connected to the vessel. And this was a test because this is not going to be an easy job to install them. They're quite stiff. One is not maybe so stiff, but by the time you have lots of them, they're tricky enough. And there are many more clips to be done. But you see how they've already welded bosses, and they've already welded some clips on the vessel. This is the diagnostic hall. This is pretty much ready now to go to the next step. These are penetrations that we're spending a lot of time working on because they have to be closed relatively soon, and we are looking at installing parts that go onto the ceiling onto these embedded plates. There's a lot of excitement about that, let's say, a lot of pressure on for us to get that done and for all your DAs to deliver the stuff that you need to go in this place because it becomes trapped. There are many pipes going through here, so at the moment it looks nice and empty, but give it a few months and suddenly this will be completely full of big pipes. I showed you this picture before. I think I like to show this picture in an INC meeting because it shows my vision of everything, how everything works. This picture was done a couple of years ago, but it's still, I think, quite valid today. So all the INC stuff is feeding in together into some sort of common highway, real-time exchange. You send the data, you ask for data, you can do analysis. We give everything to the plasma control system. And of course, there are various decisions and discussions to be made here. And okay, and there's a real-time framework software being developed for ITER, and I hope everybody's using it. Okay. So the reality is dawning. I think you can see that since last year, COVID and all, a huge amount of work has gone on in ITER. I think the main building construction is now finished. The tokamak construction is getting into full swing, and we are feeling the pain of this. Diagnostic installation has begun. We have already installed a few diagnostics. And in fact, George has installed diagnostics also in the TF coils that are coming from Japan and Europe. So one of these TF coils has the Rogowski coil fully installed, and it's actually on the high seas now on its way here. We have cable trays, wiring, penetrations, and many systems are being installed. They're all now gaining momentum and pressure indeed on all involved here and around the place. You may have heard us ringing up asking for some particular things that are needed urgently. Well, you can understand now why that's the case. So we have some high quality INC FDRs already, at least one a few weeks ago. So I hope that sets a good way forward for everybody. So I'm sure that INC will play its role too, and this is gathering the way now to share all. I think this gathering is a great way to share all the developments and good solutions together and make sure that we're all on the same page and ask questions if needed. So I wish you a successful workshop, and I now hand back to the organizer. I'm not sure if that's George or Stefan. I think George is the chair.
So we finished 8 minutes early, so if somebody wants to ask Mike something, now's the time. No? Well, thank you, Mike, for this introduction. I think the next speaker is Arthur with Bertrand to discuss to give us an explanation of the integration phases of INC. Now, yes, who is presenting of the two? There's two names here. Is it Arthur?
I will start and Bertrand will finish the presentation.
You can go ahead. I think we're only a minute early, so go ahead.
Okay, so I will provide together with Bertrand an explanation of the integration phases. And for that, okay, I will start with this figure that we have presented already many times, and that is present on the SharePoint. And I will go point by point on each of these phases and explain a bit more. And we will see that this figure is not totally correct because we are going to change a few things. So I will mention, and at the end of the presentation of my part, I will present the new scheme. So the first part is the installation on site. So all the site delivery should be managed by the DAs. You should know already, and there is I just put a link to explain the DRR, which is a milestone for delivery readiness review, and there is a instruction for that. So you should get knowledge of this, and there will be some. It's not an official review, but it's a document review to make sure that all the delivery is well managed. For the site reception and assembly, it will be managed by IO. There are two main parts: the cubicle installation, so it's managed through the EWP and CWP process, and the cable pulling and termination work. So this is managed not by PBS 55, it's managed by PBS 44. So we may be asked to provide termination diagrams and cubicle wiring diagrams quite in advance. So that's why we need to start thinking of this part already. So then on the scheme, we have always put pre-SAT, and it was written as a repeat of FAT at IO premises. And a lot of people understood that as a kind of obligatory step, but it is not at all a mandatory step. What we need to do is only to repeat part of the test, which if it was not successful. But if the FAT is completely successful, so what we expect, this pre-SAT will be limited to inspections, tests, to ensure that no damage occurred during the transport. If we need to do some power-up, we have to think that there is a need for electrical safety inspection, which is mandatory. And if needed, we could have this step done not on the site, but before on Corbière, for example, or before the real installation. So if we have some troubles, we can organize this. For the SAT, so according to PCDH, the SAT is intended to check conformity with IO requirement of the plant system procurement first as a standalone system. So in this sense, this is already what we are doing on FAT, but what is completely changing is that for the plant system, according to plant system INC integration plan, when we do the SAT, we do a complete reinstallation procedure. So all the software will be removed, and it will be taken over by Kodak integration people. So we have to think that this test it needs to be done with the very clean documentation and a final configuration. So we do not expect to have additional tasks to be done on site. And according to this plan, there are 3 steps: the component test, system test, and finally the connection to the central INC infrastructure. But this we will discuss just after. We think that it will be better to do it from the beginning. So what is the test environment? So we will have the INC cubicles, and they will be interconnected. For the detector, sensors, and actuators, it can be done partly. So it will depend on each system and depend on the installation schedule. So if the sensors are already connected, installed, and functionally operable, we will be able to test them. And originally, the Kodak infrastructure was planned to be done at the end. For the system commissioning, that's the complete commissioning of the system. So it is done from central Kodak. So the mini Kodak will be for sure removed, and there will be the full integration of the sensors, actuators, and detectors. And it is managed by PBS 55 TRO. There is one document, system commissioning plan, that should describe this. And after, we have the operation and maintenance phase with ITER integrated commissioning and operation and maintenance phase. So there is this document. I put the reference which provide this scheme for first plasma and explain the difference between the system commissioning, which ends up here, and the integrated commissioning. So integrated commissioning means that it is several PBS working together to do some overall activities. So diagnostics system commissioning is indicated here, and there will be additional diagnostic tests during integrated commissioning before VV pump down and then with vacuum. So that's just to clarify some wording. So what I mentioned earlier is that the Kodak integration, as agreed with Bertrand, should be done before the SAT is performed for several reasons. The first one is that we will have the main reason is that we cannot afford to do a lot of test campaign on site. The site condition will not be the best condition to do a lot of tests. We will have very tight schedule, very not limited, but we will have a work permit process, so we cannot go to the site as much as we want. So we need to limit to the strictly minimum activity. But it has also advantages, and one of the advantages is the availability of the data archive and data access from Kodak, which will be available when we do the SAT, and we will have the real role-based and condition-based access control. And when we will be on a ITER site, we need, during the SAT, to require strict configuration control in place. So we cannot do a change of software as we want, but we still have the possibility to access to SVN and to the development environment, even if we're in pause, to facilitate some software change when it is controlled. So finally, the new scheme is almost the same. It's just some clarification. So the first clarification is about the pre-SAT, which is not a full repeat of the FAT, but a partial and to be done if needed. The SAT has changed because we start from the integration with Central INC, and we clarify that's the integration with the sensor, detectors, and actuators will be only partial and to be decided according to the site installation schedule. And finally, the system commissioning and other steps do not change. It was already correct. And the only thing we change, so during SAT, we will be already integrated with Kodak. The integration with sensor will be partly, and system commissioning, we have the full integration with sensor. And if we need some testing with plasma condition, it will be done during ITER integrated commissioning. So I will leave the floor to Bertrand for the next slides.
Thank you, Arthur. I will delegate the changing slide to you if you don't mind.
It will be
but we have a few things. So thank you for this, Arthur. I think it's important. The message that you gave is very important. That we do the integration to Central INC as early as technically possible for various reasons. The tight schedule, as you mentioned, but also the fact that we have actually additional capabilities after integration, which are welcome, even even for SAT. What's important to know as well is that this is not just proposed in the air for diagnostics. This is what is currently in place for all plant systems. And you know, we've already integrated and we operate several plant systems, and we've performed this integration before the SAT, and this has actually been proven to be useful and successful. When we talk about Central INC, obviously we come naturally to the problem that the availability of the control building has been delayed. And so to enable this SAT commissioning, integration, and so forth, in absence of the building 71, the control building, we have several years ago decided to deploy temporary control room and temporary control system infrastructure in various buildings. So you see what we currently operate now. So we have already systems integrated to Central INC in building 38 for the reactive power compensation, in 36 for electrical distribution, 32, 33 for coal power supply, and cooling water in building 61, cooling water and utilities. And the schedule here is not quite right. For cryogenics, we are finishing it, so this is early 2021. But you can see that we talk about having quite large-scale infrastructure available in building 74 for the vacuum magnets, tokamak, cooling water, diagnostics, fueling, and so forth. And this is already scheduled for next year. The reason being that we are, as Mike said, and even with the support of pictures, we are there yet. Huh? So thank you. We can change slide. So for you to understand, this is when we talk about the temporary infrastructure. We talk about basically replicating over these interconnected systems the full Central INC. So the picture here shows what we've put in place for building 36, 38. But in the case where plant systems also interface not only to Kodak but also interface to the interlock system, we also have solutions where alongside these conventional servers sit also central or elements of the central interlock system. So what's important to note here is that we have full data flow from what you know is your plant system, from the PSH, from the fast controllers, over central interlock network, SDN, DAN, PON, we have TCN, up to basically, if we talk about archive, the data flow up to the IT infrastructure for permanent storage. So we have all of that in place in each building. This is the bottom part of the diagram, plus the office building 72 for all the services that are required to operate this temporary main control room that we have here in the building, office building, and also data access, remote data access from the IT world. We can change as well. Okay, so this is just an indication of the functions that we set out to fulfill with this temporary control infrastructure. I highlighted those which are actually not available when you are in standalone on your integration kit with the mini codec, and which are actually quite important also for SAT. So we can maybe highlight the fact that we have full data handling with permanent storage available through IT, and we have full data handling, including therefore archiving, storage, and access, also for DAN. Arthur mentioned that already. We have in place role-based and condition-based access control. So the plant systems are operated by identified users, which are authenticated using their ID and password, and then authorized or not to control the machine. You understand this is important for operating high voltage equipment, but this is important for any type of equipment. We have also alarm handling, including SMS and email support. And obviously, from the moment the data is being archived in IT, we have archive data access from the office to become very soon data access from anywhere through remote participation. Next slide, please. So this is a few words about access control, but I think we've already mentioned that. So after integration to central INC, there is no more codec dev anonymous user. All users are identified. All users are authenticated and authorized. And since we know who the people are, we also know what role they have on this project. And we can therefore enable or disable control capability. So what we've put in place is that obviously everybody is able to access for monitoring anything, but control requires to belong to authorized group. So this is what we mean by role-based access control. We have also the notion of condition-based access control. So controllability of part of the plant can be enabled or inhibited also based on machine condition. So we have an example for the 400 kilovolt where currently we have a physical local remote switch, the position of which can be changed to actually enable or disable controllability from the main control room. But in the context of diagnostics, you can think of obviously much more elaborate conditions by which we want to avoid operators to actually operate part of the machine. This is managed through access control lists, which are fully under version control. Next one, please. This is, I think this is an important aspect. Arthur mentioned it. So configuration control is very important. This is not about controlling what's happening. This is also about making sure that any test, any operation we do on the machine is done on a repeatable environment. So you all know that we use version control, that plan system INC artifacts are being delivered to Subversion. What's important for you to understand is what's happening afterwards. So when you deliver to Subversion, we have a control model where all these deliverables can be tested before they are deployed in POS. What's important to note is that it's not because you are in POS and you are integrated that you lose capability to perform changes. Obviously, we all know that that commissioning implies probably a lot of software changes. Functions will have to be modified, INC functions will have to be optimized, and we want to facilitate that. So through the central INC, even in POS during commissioning phase, you have access to development environment, you have access to SVN, and you can follow a robust configuration control process by which you can obviously test your version, your software on your plan system. You can change it in a controlled fashion using SVN available in POS to submit back a new tag for to close the full chain of quality control verification on the SCM before it's rolled out again in operation. Next one, I think we are at the end. This was just an example of a permanent archiving. So you can see here that so this is a MATLAB plot. So you have evidence here of someone using MATLAB on his office computer to actually access old 2-year-old data, if I remember, a bit more than 2-year-old data, to actually plot the data. So this is the proof that permanent archive is already in place, and access to archive data for some form of processing. Here, this is engineering processing, not scientific, but is already in place thanks to the integration. And I think this was the last slide.
Yes.
Yeah. So I think we are happy to take any question you may have on this subject.
Okay, so we're open for questions. I don't see any. Do I see any raised hands here? I don't see anything in the conversation. So does anybody have any questions?
I got a question. Might be a little bit tricky. We plan to use Git instead of SVN. Is there a mechanism to do this iteration on development in XPOS and then transfer to POS?
Yes, no problem. So if we can go back to this version control and software delivery, that big loop with the big arrow, which is happening here, that depicts how this is done and facilitated through having SVN available both publicly and also in POS. So if you do development on Git, today Git is only available XPOS, but you still deliver to Git, you still tag in Git, and then so this is the submit part. The extract, deploy, package, and so forth is also available with the Git infrastructure. But today we do not have a replica of the. We do not have a Git repository inside POS. But if that's a requirement, this is not more complicated than what we've put in place for SVN. It's just a different brand, but the concept is exactly the same as Subversion.
Okay, because we could add a SVN mirror repository for the releases if needed, but it's just to plan ahead.
Yes, no, I think that's an important point, Daniel. It's the reason why it's not done so today is that Git currently is used but by a minority of projects, those which are very collaborative in nature. And a technicality, which is that Git is provided only through IT, while Subversion, since it's provided by Kodak, is easily made available outside POS and inside POS. But we all know that Git might become much more important in the future, and the same type of infrastructure can be made available. Again, it's only a technicality.
Okay, good to hear. Thank you.
Bertrand, one of the requirements from PCDH is that during testing everything gets compiled from source code, and the code will be validated. Let's assume you have a LabVIEW FPGA or VHDL firmware project. Where would you do this in this chain?
That's also interesting. We need to go back to the slide which zooms in the TCR infrastructure. I think this is the previous one. Yes. So this is the architecture we've put in place inside POS in Building 38 for these plant systems, which are primarily industrial automation. You can see that we have in there both Kodak core system development workstation on that corner, but we also have a Windows server machine for running TIA Portal Step 7 to support doing controlled software changes on the PLC. That's that one. So that's already a Windows machine. There is no reason why for plant systems that require FPGA development, we don't also have LabVIEW in there. The important message is that the LabVIEW in there is has access to Subversion, so you can inside POS there for control changes, check out your LabVIEW project from Subversion, modify it on the TCR, compile it on the TCR, deploy it for test before you resubmit to SVN for proper handling of the sources through quality control, quality assurance, and therefore eventual packaging, signing, and so forth. So that loop that you can close locally inside POS with sources, after you are satisfied with the change and commit back to SVN, can go through the whole cycle again of being picked up by people to do a full qualification if necessary.
But when you say LabVIEW, you mean LabVIEW FPGA. Just to be clear, some people may confuse it with LabVIEW. And it must be a certain version of LabVIEW FPGA which you maintain. But if someone comes with VHDL code and other compilers, do they need to provide it with their plant INC, and you will install these compilers in your infrastructure?
Yes, so thanks for bringing these difficult questions on, Stefan. So yes, so we provide, ITER.io provides all development and toolkits for all the standard components. But for the components which are non-standards, then there is a PCDH requirement indeed that ensures that the plant system is delivered with all the documentation and all the tools required for basically configuring and recompiling the plant system from sources. So if that's the case, then yes, we assume that these tools are delivered with the plant system, and we will have to find a way to make them available. Also,
yes. I have a question concerning licenses. So let's assume that we need a pivot of filings. So does ITER provide the license, or this must be provided by us? Or how this look like?
Well, it looks to me like it's provided by you. I think this is more a question to Arthur.
Yeah, in this case, Darius is working for IO, so it's either IO Diagnostics or IO Kodak to provide the license. But yeah, in general, if we are not using standard Kodak tools, we need to find a way which is suitable, and this I think it's part of the codes checklist. Maybe I don't know, Stefan, if it's there, but it should be. So if we are using non-standard equipment, we should ensure that all the required license are provided with the system.
Okay, so maybe I have different question. So do we have any list of the standard ITER tools and also versions? I mean, for example, which version of LabVIEW is standard for ITER?
Yes, I propose you read the PCDH satellite document that include that list, and you come back to us if you think that something is missing.
Okay, and this list it's updated because these tools are changing every year. So this is updated or frozen at one moment?
It's updated, but not necessarily as fast as you would like it, Darius.
Okay, so I need to look because we are actually touching LabVIEW, and I have also quite a lot of questions which version should be used. But I will look first in the PCDH.
Yeah, I think I remember currently it's a 2013 version, but we will check it. Yeah.
Yeah, so this is very, very obsolete.
Yes, I know. So maybe if Petri is not there, maybe or he would know. But we'll put this an action item to provide a link to the documentation what versions should be used.
You see, 2013 it could be even difficult to install on the computer with Windows 10. So I have the doubts that this will.
I think that's a mistake. I think the current standard is newer than 2013, but it's certainly not the version that was released a few weeks ago.
Yeah,
Okay.
I think it's every 5 years roughly we update. So maybe it's a 2018 now. I remember from simply a few years ago.
Okay.
Can I add one question about plan system hosts on this diagram? Hello, can you hear me?
Yes, we didn't quite catch the question.
Okay. On this diagram, plan system hosts are virtual, yes?
Yes.
Transferred to TCR from real machines in cubicles, yes?
Yes.
Okay, thank you.
Yes, the computer that you have in your integration kit that runs both mini Kodak and the PSH is, there was another slide with that, but I didn't put it in, but there's a slide illustrating the fact that computer is removed with integration with Central IC. So yes, indeed, the mini Kodak disappears. I guess this was mentioned by Arthur. And then the PSH is virtualized and integrated into the central infrastructure.
And one detail, these computers will be removed physically or just disconnected, but IPC will be in the cubicle.
So normally the computer is on loan by Kodak, so it is supposed to be given back to Kodak. So.
Thank you.
But just to clarify for me, it's not going to be physically moved into your server room, right? You're going to virtually move it.
It's virtually moved. Actually, we don't. Just to make it clear, we don't move the PSH. We regenerate the PSH from version controlled sources. So it's not like we migrate the PSH that is in your industrial computer into another infrastructure. We actually get rid of this integration kit computer, and we re-instantiate the PSH with your version control sources inside infrastructure. This is why it's important to have all software delivered.
And the physical computer is given back to Kodak, which can erase it and change it for a new system, which will be for later phase.
In some cases, the computer was physically removed from the cubicle. In other cases, it was left in to be repurposed for another function.
And one more question about flow controllers and plant logic controllers, IOX. Will be migrated to virtual system hosts by Kodak team, or because as I can see, we have plant logic controllers IOX deployed on plant system hosts, yes, and after migration, after transfer of plant system hosts, after UAV vision to central system, we need to migrate them too.
Yes, so the PSH with all its processes is migrated to the central infrastructure. That includes also the processes that interface to your slow controller.
Yes, thank you.
So it's exactly the case that you see here for the one, for instance, which is util LV2 or Bill B38. These are PLC-based systems. And you can see that all the software is moved to these virtual PSH instances afterwards.
Okay. I think that's the end of that discussion, unless somebody has one last thing to say. Then we have a discussion on something relating to December. Now, a bit of a disadvantage because I wasn't there for the December session. There was some demonstration of SOUP.
SOUP config, yeah, the configuration tool. And,
who's going to lead this discussion? Is it Walter?
Walter?
Yeah, so I'm not presenting anything. I'm only here for the questions. So I don't know if there is any slides related to this demonstration from SOUP config. If you have some slides of that, Stefan.
We have uploaded the slides in the folder. So let's see, in the chat field we have no questions. Does anyone have questions concerning this configuration demonstration we had in December? If not, I can ask.
We have a little question about subconfig, but I think it's a quite common question about the usage of this tool, not only for programmers and for future users of system, because we think that for different diagnostics we have some different experimental and test configuration developed before and edited in the process at the first stages. So we want to know how can we use this tool in maximum user-friendly way to configure our HMIs and lower-level parameters for diagnostics. And one more question about, I think not only subconfig, but about current configurations of high-level software. Can we have something like history for different variables in future, and how can we access this information to have the history of some changes in our HMIs and configs?
So
yes.
Walter, you have the link to the slides. It's there in the folder, yes. in the chat field. Maybe you can explain a little bit.
Yes, I'm opening it, and I will present. Yeah, tell me maybe you see my screen.
It's loading.
Correct.
We see.
Loaded.
Yes. So can you see it?
Yes.
Okay.
Yes.
Yeah. So before answering, so this is a kind of a general overview of. I don't know if I want to present this or one of these next slides. Yeah, so the main thing in plant INC configuration, so with SOUP is to have, well, there are actually four different goals that were aimed at during the design of subconfiguration, which is to have structured configuration, so that you do not need to, or that you are not forced to configure your systems process variable by process variable, but that you can do structured configuration, meaning that you can configure whole chunks of data in one go. The next is the provision of having transformation and validation codes. I will say a little bit more about that maybe afterwards. Number 3 would be transactional loading. So you want to have certainty that if you load a big chunk of data, that the data that is loaded into your plant system or your diagnostic system is exactly as it was meant to be. So there is a way of providing hashes over this data and checking these during configuration. And it also has to be, of course, scalable from the central INC side, so that it's less of concern to you, but more to central INC, where you want to have a parallel configuration of multiple systems, and you don't want to be blocked by one system to configure other systems. So to say a little bit more about this CVVF or transformation and verification framework. So the idea here is to be able to provide configurable transformations of configurations. So I don't know if that answers the question that was the first question that was asked there. So because you asked something about also configuring HMIs, but the main idea is well, you configure plant system INCs, you do not configure HMIs in a sense. So you configure your plant system INC, and the input to this configuration can be very high level. So in the extreme case, you could imagine having only 2 modes of operation for your system, and you just have a small flag that you need to set in your high level configuration to say choose mode 1, choose mode 2, something like that. Of course, in practice it will be much more complex, but the idea is that you can go very extreme in setting a very little high level information that needs to be transformed then towards the detailed configuration of your system. So this can involve quite some complex transformations, of course, because it might include information from other plant systems even to be able to deduce that those low-level configuration parameters from these high-level modes. But in principle, this is all very flexible, and it's not so that you need to define beforehand, okay, so these are my high-level configuration parameters, and we'll have to stick with those for all kinds of operations, so also for testing, for commissioning. So that is not necessary. In principle, you can devise multiple high-level sets of information that are transformed in different ways during different workflows. So I don't, does this answer the question, or?
Not clear for me.
Yeah, I think the question was also in the direction if someone is not a programmer, just a physicist, and wants to use the configuration tools, does it require programming skills or not?
At some level it will, but I imagine that someone with no programming skills would be more involved in the definition of the high-level parameters to configure, and not necessarily in the transformation codes themselves. Although there is a way, you don't need necessarily C++ or things like that, because there's also so the transformation and validation codes can be implemented currently in MATLAB, C++, and Python. This could be extended. So I don't know if that covers all the use cases, but at some level, if you do complex transformations, you will need some tool, whether it's MATLAB or a programming language directly to be able to write those.
Sorry if I repeat some topic, but can you give us links to most to newest documents about plant NC configuration and stuff? Because I think we can try with in some near future and come back with questions if it's possible.
Yeah, so I will send here in the chat, but I will also put it in the workshop folder, the documentation for subconfiguration.
Okay, so we can find it. Okay, thank you.
Okay, yeah, I will add it. I'll put it here.
Maybe Walter, question from me. We are documenting much of the diagnostics plant INC in Enterprise Architect. And we are also thinking to document algorithms like for transformation. Would you see in the future a possibility to take this information from the Enterprise Architect file, where the structures could be defined, where the transformation algorithms could be defined, and then have a smooth process to extract this information and convert it into configuration tools?
Yeah, so I think from the system engineering point of view, this would be almost an ideal situation where you start from design documentation in a tool like Enterprise Architect, and you transform this directly into the type definitions and the transformation that are necessary and the validations that are necessary. So in principle, this is not, I mean, the Enterprise Architect is quite easy to mine and to generate different stuff from this. So this could certainly be done, yes.
If I may, I don't think that André Neto is with us, but if he is, I think this was exactly demonstrated by André during the FDR of magnetic diagnostics, where he has shown that through his model-based system engineering tool is also generating the plant system configuration code and interfaces.
Yes, I think I remember this. We still have a cheat outstanding from that review, I think.
I have another question, maybe not directly related to subconfig, but in general to SUP. Because when we are working on INC of IO diagnostics, we would like to have a possibility to configure our systems also during, for example, short-term maintenance or testing. Will SUP and subconfig will be available during these ghost phases or only during plasma operation?
No, subconfiguration is present in all phases. So if you look at the ghost states, these are all operational states during which SUP will be alive and available to use. So there is no ghost state where SUP is not available.
Okay, thank you.
Okay. Anybody else have a question on this topic?
Sounds like no.
Should we start with you, Stefan? Because you have the next talk, I think.
Yes, we can. So I will share my screen. Is it loading?
Yes, it's coming.
Okay. Can you see now my title slide?
Yes.
Okay. So about verification and validation of our designs against the requirements. I'm showing this picture here from a system engineering book from Watson because it shows that correct requirements are very important because when you try at the end to test and integrate your system and you have errors, problems with your requirements, it can propagate at the end to huge problems. It could be that some of the errors which you have in your design can be corrected. But there could be known but uncorrected errors, and the worst is unknown errors in your system. We can get back to this at the end of the discussion. I think you all know our model, V model for the system engineering, where we have the different steps, starting from requirements to design. And we have requirements for software, for hardware, and we do verification. That means we verify that our design meets these requirements, and that's what we do in the design reviews, where the panel will look at it and try to understand it. I will explain today in this presentation verification and also validation when we finally have a system installed and we have to validate that the whole system supports the requirements. I will explain also the differences between verification and validation. So the verification is mainly about, are we building the product right? So we check that the requirements are met, and we perform this during the development, and it's component and subsystem centric because it usually does not talk about the system as a whole, that each component meets its requirements. And verification methods, that's very important now, can be inspection and analysis, or when you go to acceptance testing, or engineering review. Demonstration, sometimes it's also called. And here I have a link to the source. And what you will see is that it's important that for different life cycle phases we use different methods for verification. While validation is to make sure that we are building the right product. That means the outcome of the final system. We need to check if the stakeholders' intents are met, and we do perform this validation during and or after integration for the full system. So for the verification, we had in Enterprise Architect a compliance matrix, which on the left side had all the functions, which you could expand to different levels of detail. So you can make this also more compact by looking only at the higher levels. And on the top axis, we have all the requirements, also a breakdown down to level 4. And you can imagine if you have lots of functions and lots of requirements, this becomes a quite huge matrix, and that even if not compliance need to be demonstrated for each matrix element, it can be quite huge. But let's first go back to the verification. As per the methodology which we have, for each requirement, a verification method must be provided. Until now, we used function to requirement mapping to perform a requirement verification using the engineering review method in the design. But we received feedback about the amount of work this entails because of this huge matrix which you just saw, if we map each individual function to the corresponding requirements. So what we're proposing today is a simplification, and I will elaborate on this, where instead we use only the requirement categories. Typically we have 500 INC requirements, but we have much less categories which we use in the IDs for each of these requirements. And we don't need to map all of these, as you will see, because there's overlap between the different requirements. Maintainability and operability may have very similar needs on the functions supporting them. So we only map the main requirements with using expert judgment on how it covers also the other types. And EA support will develop an add-in to support this simplified model. So if we look at the requirement categories, which we describe in a requirements breakdown, the use cases lead to maybe additional requirements which come from the use case descriptions. But then we have the huge set of functional and non-functional requirements for the conventional INC. And we may have also safety, occupational safety requirements or interlock requirements, which we treat separately. And then we did a breakdown similar to the functional analysis, but now for the requirements, where we have requirements related to signal conditioning, data acquisition system, to the measurements, like you have a measurement range, you have a measurement error, and an update rate, and so on, configuration, alarms, and so on. We spent some time on finding a good compromise on this breakdown useful for all lifecycle phases. And what you see here is the level 2 breakdown, and below the level 3. On the non-functional, you have performance, availability, usability. But these non-functional requirements also can be supported by functions. For example, availability can be improved if you can reset remotely from the control room a component to recover it. And we marked in light blue what we think could be the main functions we want to use for validation. But this is subject to a discussion and can be modified. This is not so important. So what we think is now, let's assume you had 500 requirements from PCDH, EDH, from all the handbooks, from the sub-SRDs, and so on. And you have in your system 2,000 functions. I don't want to debate whether this is now due to channel multiplicity or not. You have a huge matrix with 1 million points. And in the worst case, a full mapping would require a million pass-fail criteria, so to speak, for this validation. But when we reduce the requirements to the categories, we may have only 25. And in the functional breakdown, we may consider maybe the main functions, which are also then giving us some reduction. And at the end, if we would have a full matrix, we would have a factor of 100 reduction. But since normally this matrix is not full, we pick the most important ones, maybe the 3 most important requirements we support by a function. Then this is a huge reduction in criteria which we need for pass-fail. So now is the question, since we are doing the validation across the system and not for individual functions, I tried to make some examples to understand how this could work. For verification, now not for validation, I would check in a design. For example, if I want to look for maintainability of a system, that it is supported by, for example, self-test functions, which I find in requirements from the PCDH, or remotely controllable functions which allow me to do troubleshooting, like turning something on and off, or configuration, of course, is also part of it. Having condition flags for monitoring what's going on in my system, and having in the signal chain from detector to the measurement related functions. And operability is supported by similar things, by monitoring of condition flags for situational awareness, reset functions to recover components, and here specifically automation kicks in with the states, conditions, and events which trigger conditions, which trigger transitions, sorry. Or another example would be measurement quality is supported by health condition monitoring functions in the signal chain, quality tag components, which makes a quality tag for SDN, production state, and measurement errors I haven't seen much in designs yet, so this is also very important. That can be statistical errors, systematic errors, and so on. Performance is supported by performance measurement functions, like we have in the APIs, maybe functions which allow data throughput to then archiving. Maybe in SDN we can determine latencies. We can determine latencies from data acquisition to putting it in SDN. Timing integrity, doing cross-checks between different timestamps and or data errors. And when I look at a design, the statistics of the function groups and the variable attributes provide me a good indicator for compliance with the different requirement breakdown categories. Example for timing, what and how many functions are related to timing? What timing control, monitoring, health, conditions, events, alarms, configuration, and system management variables are available? How do they cover the different aspects of the subsystem? So when we get a INC design, I have here two examples. We run normally a statistic on the variable attributes. And in example 1, we see there's a very low number of control functions and also not so many events can happen. And some like conditions or health, I don't see at all. So I know something is missing in this design, or I couldn't find it, which supports some of these requirement categories. So the chances are quite high that some of the requirements are not well supported, and that would be brought up in the design review, maybe as a chit, and needs to be resolved. In example 2, we see much more balanced distribution of the different attributes and much richer in the different attributes. So this has a much higher potential for meeting most requirements. And then we would go into the detailed analysis and check if we have, for example, a lot of configurations, what can we configure in the different sections, or error messages, do they come only from one subsystem or component, or is it really a healthy distribution over the whole system? So this is the way from INC support how we look at designs, how they could meet the requirements. Until now I'm coming to validation. The pass-fail criteria for the functions were based on correct execution of each functions, since before we verified already that the functions support the requirements. And this had been challenged by our Russian colleagues. They said the requirements should be validated and not the functions, which I agree. We tried only to do it in a simplified way in the beginning. So from now on, the validation of the function and the requirements in context of the whole plan system is defining the acceptance criteria. So it's really an outcome-based criteria on the usability of the system. And this criteria will be then used for developing the detailed test plans with the test cases and so on in the different test scenarios. And the acceptance criteria must be written for the requirement categories as specified in the previous slides. And I think with this new concept, we will have a significant effort reduction in this validation process. So the acceptance criteria must be written in, by considering the requirements in this category as well as the supporting functions. So for each maintainability, operability, performance, I will look for these functions, and usually I find them through the variables with the attributes. Validation example for timing integrity could be, I like the timing example because many people have not spent too much effort on it. The main requirement categories for timing are performance and a DIQ system in our breakdown, the timing aspect. And acceptance criteria could be that if I have a long pulse 500 seconds or longer. And I have an option that in case of problem with my data acquisition, I can reset it, recover it, or maybe stop it. That after this action, the correct timing is reestablished in terms of clocks, triggers, and timestamps and time. Or if we lose TCN during the pulse for some reason, we could detect it and recover through exception handling, like we could switch to an internal clock. But of course, we must make sure that this internal clock is correctly synchronized before the pulse. Maybe it's at reduced performance because the internal clock has more jitter and so on. But we still will have may have a reasonable quality of the archive data for later usage. Then I have timestamps of archive data from PON. The SDN are consistent within and between plant INCs, and correlation plots are possible. I have seen in the past some examples where I tried to do correlation plots between different channels, and there was a problem because the timing was not correct on the timestamps. And maybe measurement time should reflect the time at which the measured plasma parameter observed. So if a detector has a few milliseconds, shows a few milliseconds later what the plasma did, like for example with fusion power, we do counting mode over millisecond. What is the time of the observation? Is it the beginning of this millisecond block of data, in the middle, or at the end? We need a good timing model. And then precision and accuracy should be monitored, and timing management should support the proper sequencing to make sure the readiness for the pulse is there. So in summary, in the design phase, we have the different requirements categories which we must support through functions. And we have the procedure to function mapping where we use these functions, and then we can write pass-fail criteria depending on whether we have enough functions, sufficient functions, and with the different attributes supporting the requirements. And in after manufacturing, we will test it against these. And so basically verification and validation of requirement categories may fail or may be marginal in case that the number of supporting functions are not sufficient. One should note that it's still mandatory to provide the verification method for each requirement for each phase. In the EA, we have this foreseen in the EA project. And about the testing and the test scenarios, that's the next presentation from Piotr, where we will talk more details. So my presentation was about the pass-fail criteria and the function to requirements mapping. And then in the next talk, we will hear more about testing itself. And I think that's the end of the talk. And I'm open now for questions.
Okay. I think we'll have quite reasonable time for questions. So everybody's been stunned into silence, or everybody's desperate for a coffee.
We have from FDA, I think, some moments to comment because I think we need to detail some inconsistencies between theoretical design in FDR, PDR, and FDR phases and some differences after MRR preparation, because we have maybe some our equipment difference in some cases and some topics, and maybe we have some our software from the design point of view, and because we're talking about variables and functions at verification and validation steps, we will have some inconsistencies. I think not very very bad, but in accordance with differences in real hardware and software and in theoretical design.
Yes, so that means in the process you may need to do corrections to your design or your implementations, and maybe at the end when you test your whole system you may need to make some changes. Is that what you're referring to? And then maybe the detailed test plan will change?
Yes, of course we need to do it as much as possible, but I think because we are talking about huge amount of work for years on PDR and FDR stages, some inconsistencies can be managed by our sites, ITER and DA, to have right decisions and to understand the bad or normal situation at some cases in software, hardware, and functions.
Yes, you're absolutely right. This is why I showed this diagram. We may have initially some errors in our requirements. Later, we may have some errors in the design.
Yes, and design errors, yes.
Yes, and that's why I'm showing this propagation, and that's exactly what you're referring to. We need to be very careful with this.
Yes, so I know what it is very careful way, and I just decided to comment in this case.
Okay.
Okay.
I also have a question. I understand that this acceptance criteria looks now that it's the same for all systems, as it's depending on the requirements and not on the specific functions. So then it would make sense to have this set of definitions distributed rather centrally distributed or defined by and put together somehow from a bigger team, but then distributed to everybody, or everybody needs to do it in. You see it as everybody thinking of it in his own system?
Livio, you are absolutely right. We should compile a set of validation criteria because they will be very similar for the systems. The detailed test cases for each system may be different because they have different functions. But you're absolutely right, and I have thought after preparing this talk that I will work on a repository of such validation.
Okay. Then I understood it correct. Okay.
Yes, you understood it fully correct. Yes.
But I think it emphasizes the needs also to have derived requirements. So because each system needs also we need to validate that it's fulfilled its own requirements.
Those ones will make a difference.
Exactly. So that's.
For the use cases, that may be a specific pass-fail criteria for
the derived requirements.
Yes.
Yes, I was thinking about the functional one the requirements coming from the template for all systems. Yes, not the system-specific ones.
Yes, the one for the template, we can have a standard. We can agree on some standard checks.
Okay.
Yes, and maybe if some requirement is implemented using a little bit different function in one plant INC, then maybe the acceptance criteria will change a little bit, because the acceptance criteria is the combination of requirements plus functions. So mostly it will be driven from the requirements point of view. I think if the functions are implemented a little bit different, then the acceptance criteria may also change.
So the hope is that at the end, if we have, let's say, like 25 requirement categories and a few hundred functions, we would have 12,000 mappings. But if we need only, let's say, 10% of these, like 2 or 3 from the requirements, it would bring down the number quite a lot. And we need to go through some practical cases to understand how we can optimize the efficiency in doing this.
So what is your feeling, Stefan, for such a system as you're presenting here? How many validation criteria we should have finally covered, maybe by the system test plan?
I think when I think about timing integrity, simply about acceptance criteria, maybe I have 5 to 10. We have to discuss. And if I have 5 to 10 and 25 categories, I have 125 to 250 total such statements. And then from this, the test cases need to be developed. How you want really, because this tells you how I want to. This example tells you how I want to accept it, but then you need to see how you show this in your system, in the testing, in the test case. Because demonstrating that you restore the correct timing after stopping your DIQ or resetting it requires some thinking how to do it, which may be specific for your system. Maybe you do it through archived data, or you do it through some functions you have in your system.
Did we miss a payment?
Maybe, looks like it to me. Well, I sent what you...
I think
I sent it back to you.
The answer is like 100 to 200 of such criteria we could have. And then we need to go through some examples how we want to really test it in a system.
It's both children.
Okay, so in this case, this looks for me quite realistic to provide these numbers, because when I seen on your previous slide this 2 million of acceptance criteria, it will be overkilling.
Yeah, but we never planned for a full matrix, but it's still too many.
Yeah, but you know, my problem was always to go via the whole matrix, because if you would like to really find out, you need to go each column and each row just to check if you are covering really everything.
Yes, when we did this compliance add-in 3 years ago, we expected many people to complain about this big matrix. You complained a little bit, but nobody else really complained.
Yeah. You see, for me, even as one person, it's impossible to understand and cover all requirements. So in our case, it was distributed, and you know, this is anyway very big work.
Yes, but this helped us to understand how we have to do it so that we could today propose an efficient approach.
So I like also very much the categories that will narrow a little this problem. And then if you propose some methodology for that and support from EA, it will be, in my opinion, realistic.
That's great news. But people may need to think a little bit about it, and we can have another session on this, maybe even next week.
As I said, we need some examples and some discussion how to do this in the efficient way.
Absolutely.
Can I maybe just interject here for a second? I think these kind of points need to be collected. Probably you're already doing this, collected, and then they need to be worked on, and then we need to take these actions. It doesn't necessarily all need to be on one person, but certainly we should record them with this meeting and make sure that they are followed up. Because it may be an overall saving of time, a saving of efficiency, and overall it may be good for the project.
Yes, like in the last workshop, we will collect all the actions and follow up on them.
Sure, but I think I would like to see some of the ideas are being thrown around, but I think even some of the solutions we can get from some of the people in this team. We're all on the same ITER team in the end, so any good suggestions are very valuable.
My philosophy was always to collect what people say and what they comment on these things. And
because it's getting quite exciting now, things are actually really starting to move, and this is good to see. So well done to everybody.
Yes. And I understand that people need to think a little bit about this concept before they will tell us what they think. But next week we have foreseen some time slot, so if people during this week get some ideas on this scheme, we can pick up on it next week.
Yes, could you show this slide with error propagation?
Yes.
So from this, I really see that if you have the wrong requirements at the beginning, it could be quite expensive at the end to really clarify this and improve. So this is really important to verify and at least accept the requirements at PDR or even FDR phase.
Yes, because and I think these requirement categories also will help us to reduce requirement errors, because by the categories we can use our expert judgment. We need maintainability, we need operability, we need performance. So we will not get stuck on one of the 500 individual requirements being wrong, maybe.
And some fundamental requirements could have also strong effect on the hardware architecture, and this will be this could be really difficult to correct later.
Absolutely.
So I think this also means that some categories, maybe you can highlight some categories that are extremely important and should be double-checked on FDR phase, for example.
Yes, and these categories are somewhat flexible. If you see, it's me and Sukhmit who were thinking what is the most important, but you may have other ideas, and in your test cases or in your pass-fail criteria, you may have combinations from different of these fields which support, let's say, operation is of course also supported by, let's say, configuration.
And it's also important, as you highlighted, to remember that we should verify the requirements against the whole plant system, not only INC part.
Yes, the important new thing is that what we always were thinking, that the outcome at the end for the whole system, the operational need is really supported. And that's why we changed it to validating against the outcome for the whole system going across the whole system.
Yes, so from my point of view, I think that we need more examples. As you said, with this timing, could be good to have a realistic test scenario, how this could be validated.
So why don't we both sit down and try to make an example from the timing for the pass-fail criteria and how we want to do the test cases.
Yeah. I think that's a good idea in my opinion.
Yeah, I picked the timing because that's usually a weak point in all plant INC designs. So I think if there's no more questions, you have another opportunity next week.
Yeah, we're actually on time, which is quite astonishing. Is that normal at your meeting, Stefan? I think it's the first time
if you are chairman, I have no doubts.
Wow. Okay. So I guess, is Roger here?
Yes.
No, very good. So
maybe this is the moment to make a handover 1 minute early.
Yeah, perhaps. Yes, because there's Piotr coming up.
Do you want
okay,
to
very
take a
good.
little break, actually?